What if the moment you are living right now is not special at all? What if the past you remember and the future you cannot see are just as real, just as solid as this instant? Physics has a name for this idea. It is called the block universe, and it emerges directly from the mathematics that has survived every experimental test thrown at it for more than a century. The claim is simple to state and difficult to accept. Time does not flow. There is no universal present sweeping forward, leaving the past behind and pulling the future into being. Instead, all of time exists at once, laid out like a fixed landscape in 4 dimensions. Every birth, every death, every conversation you will ever have already sits somewhere in this structure, complete and unchanging. This is not fringe speculation. It comes from Einstein's relativity, one of the most rigorously confirmed theories in all of science. And yet it collides violently with the most basic fact of human experience, which is that time clearly seems to move. So which is right? The equations that describe reality with astonishing precision, or the relentless feeling that the present is real and the future is open? For decades, this tension sat unresolved, a quiet contradiction at the heart of physics. But recent theoretical work, combined with new experimental results in quantum mechanics, has begun to reshape the question entirely. Some researchers now believe we are closing in on an answer. In this video, we will trace how the block universe was born, why it has proven so hard to escape, and whether the latest science finally offers a way out. To understand why physicists take the block universe seriously, we have to begin with an image that feels almost unnatural the first time you encounter it. Picture a river. Most of us think of time exactly this way. The present is the surface of the water where we stand. The past is the current that has already passed downstream, and the future is the water still rushing toward us from somewhere upstream, out of sight. The water moves. We stand in it. The present is the one real place, the only point where life actually happens, and everything else is either memory or anticipation. This picture is so deeply built into the way we speak and think that it barely registers as a theory at all. It simply feels like the truth. Now consider a different image. Imagine that the river is frozen solid, every drop of water locked into place, the entire length of it from source to sea, fixed in a single block of ice. From above, you could see the whole thing at once. The bend where the water was 3 miles back, the rapids ahead, the calm stretch far downstream, all of it present together, none of it moving, none of it more real than any other part. There is no special location called now. There is only the river, complete, laid out in its entirety. This frozen river is the block universe, and the strange suggestion at its core is that this second picture, not the first, is what the physics of our world actually describes. The phrase itself, block universe, was not coined by Einstein, though it grows directly from his work. It captures the idea that reality is best understood not as a sequence of events unfolding one after another, but as a single 4-dimensional object. 3 of those dimensions are the familiar ones of space, the length, width, and height we move through every day. The 4th is time. In this view, time is not a process. It is a direction, an axis, a coordinate, no more inherently dynamic than the distance between 2 cities on a map. Just as a map shows every point along a highway simultaneously, even though a traveler experiences them one at a time, the block universe contains every moment of cosmic history simultaneously, even though a conscious observer experiences them in sequence. The sequence is real to the observer, but the flow, the sense that one moment is being created while another is being destroyed, may be something the universe itself does not contain. It is worth pausing on how counterintuitive this is, because the resistance most people feel is not a failure of understanding. It is a genuine clash between what the mathematics implies and what every waking moment of human life insists upon. You did not experience yesterday and today at the same instant. You experienced yesterday, and then it was gone. And now you are here, and tomorrow has not arrived. The asymmetry feels absolute. The past is settled and unchangeable. The future is open and uncertain. The present is where you actually exist. To be told that all three are equally real, equally fixed, equally present in some deeper sense, sounds less like physics and more like a riddle designed to unsettle. And yet the path that leads here is built entirely from careful, testable, repeatedly confirmed science. That is precisely what makes it so difficult to dismiss. The story of how physics arrived at the frozen river begins, as so much of modern physics does, with the behavior of light. In the late 19th century, scientists had grown confident that they understood the broad architecture of nature. Space was a fixed stage, an absolute and unchanging arena in which events took place. Time was a universal clock, ticking at the same rate everywhere in the cosmos, the same for a person standing still as for a person on a moving train, the same on Earth as in a distant galaxy. There was a single, shared present moment that swept across all of reality at once. If you could somehow ask what was happening right now on a planet across the universe, the question would have a clear and definite answer, because now meant the same thing everywhere. This was not merely a scientific assumption. It was common sense, formalized. It was the river, made into law. The trouble came from a series of measurements concerning the speed of light. Light, it turned out, behaved in a way that no ordinary object does. If you are standing still and a car drives past you at a certain speed, and then you start running in the same direction, the car appears to move past you more slowly. Speeds add and subtract in the way intuition expects. Light refused to play by these rules. No matter how fast you moved toward a beam of light, no matter how fast you moved away from it, the light always traveled at exactly the same speed relative to you. This was not a small discrepancy. It was a direct contradiction of the most basic expectation about how motion should work. A beam of light approaching you while you race toward it should, by all common reasoning, close the distance faster. It did not. The speed stayed locked, constant, identical for every observer regardless of their own motion. This single, stubborn fact could not be reconciled with the old picture of absolute space and universal time. Something had to give. Either the measurements were wrong, which decades of increasingly precise experiments ruled out, or one of the deep assumptions about reality was mistaken. The assumption that broke was the one nobody had thought to question. If the speed of light is the same for everyone, and speed is simply distance divided by time, then for the speed to stay fixed, while observers move differently, distance and time themselves must change. Space and time could no longer be the rigid, universal backdrop against which everything happened. They had to bend, stretch, and shift, depending on motion. The stage itself was part of the play. When this idea was worked out in full, the consequences reached far beyond the behavior of light. The most profound was this. If time can run at different rates for observers in different states of motion, then the universal present, the single shared now that was supposed to stretch across all of reality, simply cannot exist. There is no cosmic clock. There is no master moment ticking forward for the whole universe at once. Each observer carries their own time, and those times do not agree. Two events that one observer judges to happen at the same instant, another observer, moving differently, will judge to happen at different instants, one before the other. The order of events, the very meaning of simultaneous, depends on who is asking and how they are moving. This is where the frozen river begins to take shape, because once the universal present dissolves, the river picture loses its foundation. The flowing river requires a single surface of water, one present moment, the same for everyone, advancing together into the future. But relativity removes that single surface. It says there is no shared now to advance. There are countless possible nows, each belonging to a different state of motion, each slicing through reality at a different angle. And if there is no privileged present, no objectively real moment that everyone agrees upon, then it becomes very hard to say that the present is the only thing that exists. The natural conclusion, the one that many physicists found themselves driven toward, is that all moments exist on equal footing. The past, the present, and the future are not stages in a process. They are regions of a single, fixed structure, and the present is simply wherever a particular observer happens to be looking from. There is a way to make this concrete that strips away some of the strangeness. Imagine a loaf of bread, a long, uncut loaf, representing the entire history of the universe along its length. One end is the distant past, the other, the far future. Now, imagine slicing the loaf into pieces. Each slice represents a single moment, a snapshot of everything happening across all of space at one instant. The old view of physics said there was only one correct way to slice the loaf, one natural set of cuts that everyone agreed upon, perpendicular to the loaf, dividing past from future cleanly and identically for all observers. What relativity revealed is that there is no single correct way to slice. An observer moving differently slices the loaf at a different angle. Their present moment, their single slice, cuts through the loaf in a way that includes events the first observer would place in the past or the future. Both slicings are equally valid. Neither is the true one. And here is the crucial point. For the slicing to be a meaningful operation at all, the whole loaf has to be there. You cannot cut a loaf that does not yet exist. The fact that different observers can slice space-time in different but equally legitimate ways strongly suggests that the entire loaf, the complete four-dimensional structure of past and future, is simply present, waiting to be sliced however one chooses. This is the logical engine that drives the block universe. It is not a mystical claim about destiny or a poetic statement about the permanence of memory. It is a structural consequence of taking relativity seriously and following its mathematics to the end. If the present is not absolute, if different observers genuinely disagree about what is happening now, and there is no fact of the matter to settle the dispute, then the most economical interpretation is that there is no objective flow at all. There is only the structure, the loaf, the frozen river, and within it, conscious beings who experience a moving present because of how they are built, not because the universe is actually moving anywhere. Of course, an interpretation is not a proof, and a great many thoughtful people have looked at exactly this reasoning and concluded that something must be missing. The feeling of passage is so vivid, so universal, that to call it an illusion seems to demand extraordinary justification. Perhaps the relativity of simultaneity tells us something about the limits of measurement rather than the nature of reality itself. Perhaps there is a true present after all, hidden from our instruments, but real nonetheless. These are not foolish objections, and we will return to them. But before we can weigh the case for and against the frozen river, we need to understand far more precisely what relativity actually says about time, because the loaf and the river are only metaphors. The real argument lives in the specific, measurable way that motion reshapes the relationship between space and time. And the man who first saw that relationship clearly, who took the strange constancy of light and built from it an entirely new vision of reality, did not set out to freeze the river at all. He set out to make the laws of physics consistent, and the timeless universe fell out almost as an accident, an implication he himself spent the rest of his life turning over in his mind. To see how a young patent clerk reshaped the meaning of time, we have to set aside the finished theory for a moment and return to the problem as it actually appeared. In the early years of the 20th century, Albert Einstein was not yet the figure who would become synonymous with genius. He was a clerk in a Swiss patent office, examining applications for devices, many of which involved the synchronization of clocks across distances, a practical engineering concern of the era, as railways and telegraphs demanded coordinated time across cities. He had a deep interest in physics, an unusual willingness to question assumptions that others treated as obvious, and a particular fixation on the troubling behavior of light. The constancy of the speed of light, the fact that it refused to add and subtract with motion the way every other speed did, struck him not as a curiosity to be explained away, but as a clue to be taken at face value. His decision was almost reckless in its simplicity. He chose to assume that the speed of light really was the same for every observer, exactly as the experiments suggested, and to follow that assumption wherever it led, no matter how strange the destination. This is worth dwelling on, because it reveals the method behind the revolution. Most physicists confronted with an experimental result that contradicts common sense will look for a way to preserve common sense and explain the result as an artifact, a measurement error, an unforeseen complication. Einstein did the reverse. He treated the experimental result as sacred and decided that common sense, specifically the common sense notion of absolute time, would have to bend. He combined the constancy of light with one other principle, the idea that the laws of physics should be the same for any observer moving at a steady speed, that there is no special, privileged state of rest in the universe against which all motion is measured. A person in a smoothly moving train, with the windows covered, cannot tell by any internal experiment whether they are moving or standing still. The laws of physics work identically either way. These two principles, the constancy of light and the equivalence of all steady motion, seem modest. Together, they detonate the entire structure of absolute time. The reasoning unfolds through a careful examination of what it means to say that two distant events happen at the same time. This sounds like a trivial question with an obvious answer, but Einstein recognized that simultaneity is not something we directly perceive. It is something we infer, and the method of inference depends on signals traveling between locations. To judge whether two distant flashes of light occurred at the same instant, you need some way to compare them, and any such comparison relies on information traveling from those locations to you. Information that can move no faster than light. Once you accept that the messengers carrying the information have a finite, fixed speed, the notion of simultaneity becomes entangled with motion in a way that cannot be undone. Consider the now classic illustration set on a moving train. Imagine a long railway car traveling at high speed along a track. In the exact center of the car stands an observer. At the two ends of the car, front and back, sit two lamps. Now suppose that, from the perspective of this central observer riding inside the train, both lamps flash at precisely the same instant. The light from each lamp travels toward the center, covering equal distances at equal speed, and arrives at the central observer simultaneously. For this observer, the conclusion is clear and correct. The two flashes were simultaneous. They happened at the same time. But now, place a second observer on the ground beside the track, watching the train rush past. This observer sees the same two flashes, but the situation looks entirely different. During the tiny interval while the light is traveling from the lamps toward the center of the car, the train itself is moving forward. The back of the car is rushing toward the point where the rear flash was emitted, while the front of the car is racing away from the point where the front flash was emitted. Light travels at the same fixed speed for this ground observer too. That is the unbreakable rule. So from the ground, the light from the rear lamp has a shorter distance to cover to reach the moving center, because the center is approaching it, while the light from the front lamp has a longer distance to cover, because the center is fleeing from it. If both beams travel at the same speed, but cover different distances, they cannot have been emitted at the same time and still arrive together. For the ground observer to make sense of the light reaching the center, as it does, the rear flash must have happened later, and the front flash earlier, or some arrangement in which the two flashes were simply not simultaneous at all. Here is the part that resists every instinct. There is no error in either account. The observer on the train is not mistaken. The observer on the ground is not mistaken. They genuinely disagree about whether the two flashes happened at the same time, and both are correct within their own frame of reference. Simultaneity, the question of whether two separated events occur at the same moment, has no single universal answer. It depends on the motion of the observer asking the question. This is not a limitation of the lamps or the eyes or the instruments. It is a feature of reality itself, a direct and unavoidable consequence of light having the same speed for everyone. The disagreement is not about perception. It is about the structure of time. Once this is absorbed, the universal present collapses, and it does so with mathematical inevitability. If two observers moving relative to each other cannot agree on which distant events are simultaneous, then there is no shared slice of now that they both inhabit. The single advancing surface of the river, the one present moment, supposedly common to all of reality, fractures into countless different versions, one for each possible state of motion. And this is not a small effect, confined to trains. The same logic applies to any two events anywhere in the universe. The faster the relative motion, and the greater the distance between the events, the larger the disagreement about their timing becomes. For everyday speeds and everyday distances, the effect is so minuscule that it never shows up in ordinary life, which is precisely why our intuitions never developed any sensitivity to it. But the effect is real, and it has been measured directly again and again, with clocks flown on aircraft and satellites, with particles accelerated to enormous speeds, with a precision that leaves no room for doubt. The deeper consequences extend beyond simultaneity into the very rates at which time passes. Relativity reveals that a clock in motion, relative to an observer, ticks more slowly than a clock at rest beside that observer. This is not an illusion produced by the difficulty of observing a fast-moving clock. The moving clock genuinely accumulates less time. Two travelers who separate, one moving rapidly through space and the other remaining behind, will find upon reunion that different amounts of time have elapsed for each of them. The one who traveled will have aged less. This has been confirmed with atomic clocks of extraordinary accuracy. Take two such clocks, synchronized perfectly. Send one on a high-speed journey by aircraft around the world, and upon return, it will read a slightly different time than its stationary twin, by exactly the amount the equations predict. Time is not a fixed background rate. It is malleable, dependent on motion, personal to each observer's path through the universe. And it is not only motion that warps time. A closely related theory, developed by Einstein a decade later, extended these ideas to gravity and revealed that time also runs at different rates depending on the strength of the gravitational field. A clock closer to a massive object, deeper in its gravitational pull, ticks more slowly than a clock farther away. This too has been measured directly. Place one precise clock at the base of a tall building and an identical clock at the top, and the clock at the top, slightly farther from the center of the Earth, will run measurably faster. The difference is tiny, but it is unmistakable and exactly as predicted. The satellite navigation systems that guide vehicles and devices across the planet must account for both effects, the slowing of time due to the satellite's motion and the speeding of time due to their greater distance from Earth's mass. Without correcting for these relativistic shifts in the rate of time, the positioning systems would drift into error within hours, their calculations thrown off by the simple fact that the clocks in orbit do not keep the same time as the clocks on the ground. Every accurate location fix is a quiet, continuous confirmation that time is not absolute. These are not abstractions argued in seminar rooms. They are engineering necessities built into the infrastructure of modern life, validated trillions of times over. And their cumulative weight presses relentlessly toward a single conclusion about the nature of time. If time runs at different rates for different observers, if simultaneity has no universal meaning, if there is no shared present and no master clock, then the comforting picture of a single moment of now, advancing uniformly into the future for the entire cosmos, cannot be sustained. The universe does not have one time. It has a web of times, interrelated by precise mathematical rules, but irreducibly multiple. And a universe without a single present is a universe in which it becomes deeply unclear what could possibly be meant by the claim that only the present is real. Einstein himself grasped where this led, and the implication seemed to settle into him with a kind of resigned clarity over the course of his life. Late in his years, when a lifelong friend died, he wrote to the man's family in terms that have become famous among those who study his thought. He suggested that the distinction between past, present, and future is only a stubbornly persistent illusion. He did not mean this as a consolation drawn from sentiment. He meant it as a statement about physics, a direct reading of what his own theory implied. If all moments exist within the four-dimensional structure of spacetime, then a person who has died has not vanished from reality. They still exist, located in their portion of the structure, in the moments that make up their life, exactly as the distant mountains still exist, even when you have walked beyond them and can no longer see them. From the standpoint of the block universe, death does not erase. It simply marks a boundary, a place where a particular life ceases to extend into later moments, while all the moments it did occupy remain permanently real. This is the vision that relativity, followed honestly, seems to hand us. It is austere, strange, and difficult to hold steadily in the mind. It tells us that the river is frozen, that the loaf is whole, that every moment we will ever live already exists, and that our sense of moving through them is a feature of consciousness rather than a fact about the world. But notice that everything established so far rests on a particular reading of the evidence. The experiments confirm that simultaneity is relative, that clocks run at different rates, that there is no universal present accessible to measurement. They do not, strictly speaking, prove that the future already exists in the same concrete way the past does. That further step, from the relativity of the present to the equal reality of all moments, is an inference, a philosophical interpretation laid on top of the physics. It is a very natural inference, perhaps the most natural one available, but it is not forced upon us with the same iron necessity as the experimental facts themselves. And it is precisely in that gap between what the experiments demonstrate and what the block universe concludes that the entire debate over the nature of time has been fought. To understand the stakes of that debate, we need to look more carefully at the geometry that relativity puts in place, the precise architecture that determines which events can influence which others, and how that architecture both supports the frozen river and quietly leaves a door open for something else. The architecture that relativity puts in place has a name and a shape, and understanding it is essential because it is the structure that determines what the block universe can and cannot contain. The shape is called the light cone, and it is the closest thing physics has to a map of cause and effect itself. To grasp it, return to the single most important fact established so far, the one that broke absolute time in the first place. Light travels at a fixed speed, and nothing that carries energy or information can travel faster. This speed is not merely the speed of a particular kind of wave. It is the universe's ultimate speed limit, the maximum rate at which any influence can propagate from one place to another. No signal, no force, no message, no causal connection of any kind can exceed it. This limit, once you take it seriously, carves the universe into regions with sharply different relationships to any given moment, and the boundaries between those regions are drawn by light. Imagine a single event, a flash, a clap, a decision, anything that happens at a particular point in space, at a particular instant in time. Call it the here and now. From that point, light spreads outward in all directions, expanding as a sphere that grows larger every instant. If you could freeze this expanding sphere and trace its history through time, plotting space along the horizontal directions and time along the vertical, the growing sphere of light would trace out the shape of a cone, widening as it rises into the future. This is the future light cone. It contains every point in space and time that the original event could possibly reach, every location that a signal from the here and now could eventually influence, traveling at or below the speed of light. Anything inside this future cone can in principle be affected by the event. Anything outside it cannot, because reaching it would require an influence traveling faster than light, which the universe forbids. There is a second cone, a mirror image opening downward into the past. This is the past light cone, and it contains every event that could have sent a signal arriving at the here and now. Everything you can see, everything you can know about, everything that could have shaped the present moment must lie within this past cone. The light from a distant star reaching your eye tonight left that star years or centuries ago, and that departure event sits on the surface of your past light cone. The sound of a voice, the warmth of sunlight, the gravitational tug of the planet beneath you. All of these influences arrive from within the past cone, having traveled to you at or below the cosmic speed limit. Anything outside the past cone could not have reached you yet, and so could not have played any part in producing the present moment. Between the future cone above and the past cone below lies a vast region that belongs to neither. These are the events that are too far away in space to be reached by a signal from the here and now within the available time, and too far away to have sent a signal that has yet arrived. They are causally disconnected from the present event entirely. Nothing the event does can affect them, and nothing they do can affect the event, at least not yet. Physicists call this region the elsewhere, and it is here that the relativity of simultaneity makes its home. For events in the elsewhere, there is no agreed-upon answer to whether they happen before, after, or at the same time as the here and now. Different observers, moving differently, will slice through this region at different angles and reach different verdicts about its timing. The light cone structure tells us exactly which events have a definite, observer-independent time order with the present, those inside the cones, and which do not, those in the elsewhere. For events connected by the possibility of cause and effect, lying within each other's light cones, every observer agrees on the order. The cause always precedes the effect, for everyone, regardless of motion. Relativity scrambles simultaneity, but it never scrambles causality. The flash always comes before it could possibly influence anything in every frame of reference. This is the deep consistency that keeps the universe from descending into contradiction. This distinction matters enormously for the block universe, because it tells us precisely how much freedom the relativity of the present really grants. When different observers slice the loaf of space-time at different angles, their slices rearrange the timing of events in the elsewhere, the causally disconnected region. But they can never rearrange the order of events linked by cause and effect. A slicing that put an effect before its cause would be physically impossible, because it would describe a universe in which signals outran light. So the geometry imposes a strict discipline. The block universe is not a place where anything can be reordered to anything. It is a structure with a fixed causal skeleton, an unchangeable web of which events can influence which others, overlaid with a flexible scheme of slicing that only reshuffles the timing of events that have no causal relationship at all. The loaf can be cut at many angles, but the threads of causation running through it hold firm no matter how you cut. The light cone, then, is the universe's enforcement of cause and effect, written into the geometry of space-time itself. Every point in the four-dimensional structure carries its own pair of cones, its own future of reachable events, and its own past of events that could reach it. Trace the cones forward and backward, and you map out the entire causal architecture of reality, the complete network of what can affect what. And here, the block universe interpretation finds some of its strongest support, because this causal structure is most naturally understood as a fixed, timeless geometric object. The light cones do not move. They do not flow. They are simply features of the landscape, like the contours of a mountain range, present everywhere at once, defining the relationships between all events, whether those events are in what we call the past or the future. To describe this structure as evolving, as being built moment by moment, adds nothing that the geometry itself does not already contain. The cones are just there, the whole web at once, exactly as the frozen river picture suggests. There is a way to feel the strangeness of this through scale, by considering how the light cone shapes our relationship with the cosmos. Because nothing outpaces light, and because the universe is vast, the past light cone of any observer on Earth reaches out across enormous distances, and the events it touches grow older the farther out it extends. When you look at the sun, you see it not as it is now, but as it was about 8 minutes ago, because that is how long its light has taken to cross the distance to your eye. The sun, you see, sits on your past light cone, 8 minutes deep. When you look at the nearest star beyond the sun, you see light that left it more than 4 years ago. When you look at a distant galaxy, you may be seeing light that began its journey before the Earth existed, light emitted by stars that have long since burned out. Every glance at the night sky is a glance along the past light cone, a tour through a sequence of moments stretching back across the history of the universe. None of them the present moment of those distant objects, all of them moments that the geometry of space-time holds permanently in place. You never see the universe as it is now. You see a nested series of pasts, each at the distance light requires to reach you. The now of a distant galaxy is forever inaccessible, locked in the elsewhere, with no fact of the matter about how it lines up with your own. This has a consequence that sharpens the block universe argument considerably. If there is no meaningful shared present between you and a distant galaxy, if the question of what is happening there right now has no objective answer, then it becomes very difficult to maintain that only the present is real. Real to whom, and according to which slicing? The galaxy's events are perfectly definite. They occupy specific locations in the space-time structure. They influence and are influenced according to the strict rules of the light cones. The only thing that is not definite is how they line up with your personal now. And that indefiniteness is not a sign that they are less real. It is a sign that now is not a feature of the universe at all, but a feature of a particular observer's slicing. Strip away the observer-dependent slicing, and what remains is the structure itself, complete and timeless, with every event equally present, in the only sense that the physics actually supports. And yet, precisely here, a careful thinker begins to notice the door left ajar. The light cone structure establishes that causally connected events have a fixed order for all observers. It establishes that causally disconnected events have no universal order. But notice what it does not establish. It does not, by itself, tell us that the events in the future light cone already exist in the same way the events in the past light cone do. The geometry is perfectly compatible with the frozen river, in which the future is as solid as the past. But it is arguably also compatible with a different picture, one in which the past and present are fixed, but the future cones point toward events that have not yet come into being, that are still genuinely open. The mathematics of relativity treats past and future symmetrically, drawing both sets of cones with the same confident strokes. The question is whether that symmetry reflects a real symmetry in nature, with future events just as existent as past ones, or whether it is a feature of the mathematical description that does not perfectly mirror reality. The equations do not care about the difference. They work identically either way. But reality might. This is the gap that no experiment has closed, and the reason the block universe remains an interpretation rather than a proven fact. The relativity of simultaneity is real and measured. The light cone causal structure is real and measured. The slowing of moving clocks, the warping of time by gravity, all of it is confirmed beyond reasonable doubt. What is not confirmed, what cannot be directly measured, is the ontological status of the future. Does it exist, fully formed, waiting for us to arrive at it? Or is it a region of the structure that is still being determined? The block universe says it exists, but the geometry alone does not force that conclusion. It permits it, even encourages it, through its elegant symmetry, but it leaves the final verdict resting on an inference about what the mathematics means rather than what it directly demonstrates. To probe this gap further, we need to do more than admire the geometry from outside. We need to step inside it and ask what happens when an observer actually moves through this structure, when the angle of their slicing shifts even slightly, and how dramatically that shift can rearrange what counts as the present across cosmic distances. Because the relativity of simultaneity is not just a subtle correction to be applied to fast trains. When the distances involved grow large enough, the effect of even a gentle, ordinary motion becomes staggering, reaching across light years and shuffling the present moment of entire worlds. There is a thought experiment that makes this concrete in a way that the abstract geometry never quite can, one that takes the calm mathematics of slicing and reveals just how radical its implications become when the scale is cosmic. It begins with something as mundane as a person deciding which way to walk. The thought experiment that makes the slicing of spacetime concrete is often built around a distant galaxy, and the galaxy usually chosen is Andromeda, our nearest large galactic neighbor, lying roughly 2.5 million light-years away. The choice of Andromeda is not arbitrary. It is far enough that the effect becomes dramatic, yet it is a real, familiar object, a faint smudge of light visible to the naked eye on a dark night, containing 1 trillion stars and presumably whatever else a galaxy of that size might contain. The experiment asks a simple question with an unsettling answer. What is happening in Andromeda right now? And it shows that the answer depends, to a degree that defies intuition, on something as trivial as whether you are walking toward the galaxy or away from it. Set up the scenario carefully. Imagine 2 people standing on a street, side by side, at the same spot on Earth. One of them is standing still. The other is walking at an ordinary leisurely pace, the speed of a casual stroll, in the direction of Andromeda. They are at the same place, essentially the same moment, separated only by their state of motion, one at rest and one walking slowly. Now apply the relativity of simultaneity, the principle established by the train and the lamps, the principle confirmed by every precise clock ever flown or compared. Because the 2 people are moving differently, they slice the loaf of space-time at slightly different angles. Their present moments, their now slices, are tilted relative to each other. For events nearby, on Earth, or even across the solar system, this tilt produces a difference so small it is utterly undetectable, a fraction of an instant. But the tilt is an angle, and like any angle, its effect grows with distance. Extend that slightly tilted slice across 2.5 million light-years, all the way to Andromeda, and the tiny angular difference becomes an enormous separation in time. The numbers, when worked out, are genuinely startling. The person walking toward Andromeda has a present moment that, when extended to the galaxy, includes events there that the stationary person would place in the future. The person walking away has a present that includes events the stationary person would place in the past. The difference between the two slices, projected across that vast distance, can amount to days. The walkers now in Andromeda and the standers now in Andromeda can be separated by the events of several days within that distant galaxy. If something momentous were unfolding there, a decision, a departure, the launch of a great fleet, the two people standing on the same street corner on Earth would, according to their own equally valid slicings, place that event at different times. For one of them it might lie in the future, not yet happened. For the other, it might already be part of the settled past. And the only difference between them is that one is walking and one is standing still. This is the heart of what makes the thought experiment so forceful. The motions involved are not exotic. We are not talking about spaceships near the speed of light or particles in an accelerator. We are talking about walking, the most ordinary motion imaginable, the kind of thing every person does without a moment's thought. And yet that ordinary motion, projected across cosmic distance, is enough to shuffle the present moment of an entire galaxy by days. The relativity of simultaneity is not a special effect reserved for extreme conditions. It is woven into every step you take. Every time you change your speed or direction, you re-slice the universe, and the distant present rearranges itself accordingly. For nearby things, the rearrangement is negligible. For distant things, it is profound. But the principle is always operating, always, in every motion of every object, everywhere. The conclusion that the architects of this argument draw is direct and difficult to evade. If the walkers present in Andromeda includes events that have, for the walker, already definitively happened, then those events must be real. They are not pending. They are not waiting in some undetermined limbo. They are part of the walker's settled now, as concrete as anything in the walker's immediate surroundings. But for the stationary person standing right beside the walker, those same events lie in the future, supposedly not yet real, not yet determined. Both people are equally correct. Neither slicing is privileged, and the only way to reconcile their equally valid but contradictory accounts of what is real in Andromeda is to conclude that all of it is real. The events the walker calls present and the events the stander calls future must both exist, because there is no principled way to say that one slicing captures reality and the other does not. If the walker's future-leaning slice is just as valid as the stander's present, then the future events on that slice are just as real as present ones. And once you grant that, the future as a whole loses its special status as the realm of the not yet existent. It becomes simply another region of the fixed structure, every bit as real as the present and the past. There is a particularly sharp version of this argument that tightens the logic further, sometimes presented as a chain of reasoning about what each observer considers definitely real. Suppose the stationary person on Earth considers everything in their own present moment to be definitely real, including, on their slice, a particular event in Andromeda. Now consider a second observer, perhaps an alien in Andromeda, who happens to be moving in such a way that their present slice, extended back to Earth, includes the stationary person on Earth at this very moment. By the same reasoning, this Andromedan observer considers everything on their slice to be definitely real, including the Earth person. But their slice also includes events in Andromeda that lie in the Earth person's future. The reasoning chains together. What is real for me includes you. What is real for you includes events I would call future. Therefore, those future events are real for me too, by a kind of transitivity of reality. Reality, on this argument, cannot be confined to a single slice, because the slices overlap and interlock in ways that force the entire structure to be real all at once. The future cannot be quarantined off as unreal when other equally valid observers have it sitting squarely in their present. This transitivity argument has been enormously influential, and many find it compelling precisely because it does not rely on any exotic physics. It uses only the relativity of simultaneity, which is as well established as anything in science, combined with a single reasonable-seeming assumption that what lies in any valid observer's present is definitely real. From these modest ingredients, it manufactures a startling conclusion: the complete reality of the entire four-dimensional block, past, present, and future, all equally existent. It is the frozen river derived not from grand metaphysical speculation, but from a casual walk down a street and a faint smudge of light in the night sky. And yet, for all its force, the argument has a vulnerability, and locating it precisely is one of the keys to the entire debate. The vulnerability lies in that seemingly innocent assumption, the one that says what lies in any valid observer's present moment is definitely real. This assumption sounds harmless, almost tautological, but it smuggles in exactly the conclusion it is meant to establish. It assumes that reality can be read off from a slice of simultaneity in the first place, that the present moment, in the relativistic sense, is the right thing to identify with what exists. Someone who doubts the block universe can simply deny this. They can argue that relativistic simultaneity, the tilted slicing, is a useful tool for coordinating measurements, but is not the same thing as a metaphysical present, not the same thing as the boundary between what exists and what does not. On this view, the fact that the walker and the stander slice space-time differently tells us about the relativity of measurement and coordination, not about the relativity of existence. The events in Andromeda are doing whatever they are doing, and the question of how they line up with my personal now might simply be a question with no deep significance, a bookkeeping convention rather than a statement about the fabric of reality. This is a serious objection, and it exposes the central difficulty that has kept the block universe debate alive for so long. The physics, the actual measurable content of relativity, is not in dispute. Everyone agrees that simultaneity is relative, that the walker and the stander disagree about Andromeda, that clocks run at different rates, that the light cone structure governs causality. What is in dispute is what these facts mean for the nature of existence, and that question, the ontological question, may not be one that any experiment can settle. The Andromeda argument is powerful, but it is powerful as philosophy resting on physics, not as physics alone. It takes the indisputable relativity of simultaneity and adds an interpretive premise about reality, and the entire weight of the block universe conclusion rests on whether that premise is accepted. The frozen river is not measured, it is inferred, and the inference, however elegant, can be resisted by anyone willing to hold that the present moment of measurement and the present moment of existence are not the same thing. Still, the resistance comes at a cost, and this is what makes the debate genuinely difficult rather than easily dismissed. To deny the block universe, to insist that the future is open and not yet real, one seems to need a privileged present, a true now that divides the existent past from the non-existent future, the same for all observers. But relativity has shown that no such universal present can be detected. If it exists, it is hidden, undetectable in principle, leaving no trace in any measurement. And a privileged present that can never be observed, that plays no role in any equation, that affects nothing we can measure, begins to look uncomfortably like an article of faith rather than a feature of physics. The block universe advocate can press this point hard. You want a real, flowing present, they say, but your own best theory of space and time gives you no place to put it and no way to find it. You are postulating something invisible to preserve an intuition. Why should the intuition outweigh the theory? The defender of an open future has answers to this, and we will come to them. But notice the shape of the standoff that has emerged. On one side stands relativity, with its relative simultaneity and its undetectable present, pushing toward a timeless block in which all moments are equally real. On the other side stands the overwhelming human conviction that time genuinely passes, that the future is open, that the present moment is special, a conviction so strong that to call it an illusion seems almost absurd. The physics does not obviously settle the matter, because the crucial question, whether the future already exists, lies just beyond what any measurement can reach. For decades, this is roughly where the discussion rested. A deep and apparently unresolvable tension between a successful theory and a stubborn intuition, with clever arguments like the Andromeda thought experiment marshaled on the side of the block, but never quite delivering the knockout blow, because the interpretive premise could always be questioned. What would it take to break the standoff? It would take new physics, some genuinely new ingredient that bears on the question of whether the future is fixed or open, something beyond the relativity that generates the puzzle in the first place. And there is, in fact, another great pillar of modern physics, one that emerged in roughly the same era as relativity, that seems to speak directly to this question, and seems, at least at first glance, to come down firmly on the side of an open future. It deals not with the vast and the fast, but with the small, the behavior of matter and energy at the scale of atoms and particles. It introduces randomness, uncertainty, and an apparent role for the act of observation in determining what happens. And it sits in deep and unresolved tension with the smooth, deterministic, timeless block that relativity seems to describe. Before we can ask whether anyone has truly found a solution to the block universe, we have to bring this second pillar into the picture, because the most promising routes toward an answer all run directly through the strange and contested territory where relativity and the physics of the very small are forced to confront one another. And the first thing the territory does is reintroduce, in a radical new form, the very thing the block universe had seemed to banish. Genuine, irreducible uncertainty about what comes next. The second great pillar of modern physics arrived at almost the same historical moment as relativity, and from the beginning it spoke a different language about time. Where relativity described a smooth, continuous, deterministic universe in which the state of things at one moment fixed the state at every other moment with perfect precision, the physics of the very small introduced something that had no place in the older picture at all. It introduced genuine chance, not the apparent randomness of a coin toss, which is really just hidden determinism, the outcome fixed by forces too complex to track. It introduced randomness that appears to be fundamental, built into the fabric of reality, irreducible, the kind of randomness that no deeper knowledge could ever eliminate. And if that randomness is real, if the universe genuinely does not decide certain things until they happen, then the future cannot already exist in finished form, because the future has not yet been determined. The frozen river on this reading cannot be frozen, because the water downstream has not yet chosen its course. To understand why this is such a profound challenge to the block universe, we have to look at how matter behaves at the smallest scales, where the rules that govern atoms and particles depart radically from the rules that govern stones and planets. In the everyday world, objects have definite properties at all times. A ball thrown across a room has, at every instant, a specific position and a specific speed. You may not know them precisely, but they exist, definite and waiting to be measured. The world of the very small does not work this way. A particle such as an electron does not, in general, possess a definite position until that position is measured. Before measurement, it exists in something stranger, a kind of blur of possibilities, a superposition of many different positions at once, each carrying a certain weight, a certain likelihood. The mathematics that describes this blur is precise and reliable, among the most accurate predictive tools in all of science. But what it predicts is not a definite outcome. It predicts probabilities, the chances of finding the particle here rather than there when a measurement is finally made. This is not a statement about our ignorance. This is the radical claim that distinguishes the physics of the small from everything that came before. The particle does not secretly have a definite position that we simply fail to know. According to the standard understanding, it genuinely does not have one. The blur of possibilities is the complete and total description of the particle's reality before measurement. There is no hidden fact, no concealed answer, no truth of the matter about where the particle is, until the act of measurement forces nature to settle on a single outcome. And which outcome nature settles on appears to be a matter of pure chance, governed by the probabilities the mathematics provides, but not determined by anything deeper. Identical particles prepared in identical ways, measured in identical ways, will yield different results, and nothing about their prior state explains the difference. The difference is, as far as anyone has been able to determine, simply random. The evidence for this strange behavior is overwhelming and has accumulated for a century. The most famous demonstration involves sending particles, one at a time, toward a barrier with two narrow openings, and recording where each particle lands on a screen behind the barrier. If particles were simply tiny balls, each would pass through one opening or the other and pile up in two bands behind the two slits. That is not what happens. Instead, over many particles, a pattern of many bands builds up. the characteristic pattern of waves passing through both openings at once and interfering with each other, reinforcing in some places and cancelling in others. The astonishing part is that this pattern emerges even when the particles are sent one at a time, with long gaps between them, so that each particle is alone in the apparatus, with no other particle to interfere with. Each single particle, it seems, passes through both openings at once, interferes with itself, and lands in a position governed by the resulting wave of possibilities. The particle behaves as a spread-out blur of potential locations right up until it strikes the screen, at which point it abruptly becomes a single definite point, a single flash at one spot. The blur of possibilities collapses in that instant to one actual outcome, chosen at random from the available possibilities according to their assigned weights. This sudden transition from a spread-out range of possibilities to a single definite result at the moment of measurement is the central mystery of the physics of the small, and it is the place where the conflict with the block universe becomes sharpest. Before measurement, the description is smooth, continuous, and deterministic in its own way, the blur of possibilities evolving according to precise equations that contain no randomness at all. The randomness enters only at the moment of measurement, when the smooth blur is somehow replaced by a single sharp outcome. And that moment of transition seems to introduce exactly the thing the block universe denies: a genuine before and after, a moment when something that was undetermined becomes determined, when the open becomes settled. If the future is full of such transitions, each one a genuine resolution of real uncertainty into a definite result, then the future cannot already be sitting there, complete and frozen. It must be coming into being, moment by moment, as each act of measurement plucks one outcome from the field of possibilities and makes it real. This is the picture that has made many physicists and philosophers suspect that the block universe, however elegant, must be wrong, or at least incomplete. The physics of the small seems to describe a universe with a genuine present, a frontier where possibility crystallizes into actuality, where the not yet real becomes real. It seems to restore the flowing river, with the future as open water and the present as the surface where the freezing happens. And it does so not through intuition or philosophy, but through the most precisely tested predictions in the history of science. The probabilities work, the randomness is measured, the collapse from blur to point happens reliably in every laboratory that looks for it. If the future were already fixed, why would nature need to make these random choices at all? Why would there be probabilities rather than certainties? The very existence of irreducible chance seems to presuppose an open future for that chance to operate on. But the situation is far more tangled than this clean opposition suggests, and the tangle is essential to understand, because it is in the knots that the most interesting possibilities hide. The first complication is that the moment of measurement, the collapse from blur to point, has never been fully explained. Nobody knows in any agreed-upon way what actually constitutes a measurement, or why or how the smooth blur of possibilities turns into a single definite outcome. The equations describe the blur and its smooth evolution with perfect precision. They describe the probabilities of various outcomes with perfect precision. But the actual transition, the collapse itself, is not described by any equation in the standard framework. It is simply asserted to happen when a measurement occurs, and what counts as a measurement is left vague. Is it the interaction with a large instrument? The involvement of a conscious observer? Some threshold of complexity or size? The theory does not say. This gap, the absence of any clear account of how and when possibility becomes actuality, is known as the measurement problem, and it is arguably the deepest unsolved puzzle in all of physics. The randomness that seems to threaten the block universe lives entirely inside this unexplained gap. And because the gap is unexplained, it is not at all clear that the randomness is what it appears to be. Here is the crucial subtlety. The smooth evolution of the blur of possibilities, the part of the theory that is precisely described by equations, contains no randomness and no collapse. It is perfectly deterministic and perfectly time-symmetric. Run it forward or backward, and it obeys the same rules. In this respect, it is entirely at home in the block universe, just another smooth, timeless, deterministic structure, like the geometry of relativity. The randomness, the apparent coming into being of definite outcomes, enters only when this smooth evolution is interrupted by the mysterious act of measurement. So the question of whether the physics of the small really refutes the block universe depends entirely on what measurement actually is. If measurement is a real physical process in which one outcome is genuinely selected at random and the others genuinely vanish, then the future is open and the block is broken. But if the appearance of a single random outcome is somehow an illusion, a feature of how observers embedded in the system perceive a process that is really still smooth and deterministic underneath, then the randomness evaporates and the block universe survives intact. The entire fate of the frozen river in this arena hangs on the interpretation of the measurement problem. And there is more than one interpretation, each with radically different implications for the nature of time. One family of interpretations takes the collapse at face value, treating it as a real physical event, a genuine moment when possibility becomes actuality, with all the consequences that has for an open future and a flowing present. Another family denies that any collapse happens at all, insisting that the smooth, deterministic evolution is the whole story, and that the appearance of random outcomes is a kind of perspectival illusion, preserving determinism, and with it, the timeless block. Still, other approaches propose that the randomness is real, but governed by influences we have not yet identified, possibly including influences that run backward in time, an idea that would transform the entire question in ways we will explore. The point, for now, is that the physics of the small does not deliver a clean verdict against the block universe. It delivers a profound ambiguity, a fork in the road where the same experimental facts can be read as either confirming or destroying the frozen river, depending on what one believes is happening in that unexplained instant of measurement. This ambiguity is not a failure of the science. It is a signpost pointing toward exactly the questions that any genuine solution to the block universe problem must answer. The relativity pillar pushes toward a timeless block with no preferred present. The pillar of the very small introduces apparent randomness that seems to demand an open future, but only through the unexplained mechanism of measurement, which might or might not involve genuine becoming. And the two pillars do not fit together comfortably. Relativity is smooth, continuous, deterministic, and time-symmetric. The collapse of possibilities, if it is real, is abrupt, discontinuous, random, and seems to single out a moment of now in a way relativity forbids. These two theories, each magnificently successful in its own domain, describe time in ways that appear flatly incompatible. Reconciling them is the great unfinished task of theoretical physics, and any reconciliation will inevitably take a stand on whether the future is fixed or open, whether the river flows or stands frozen. For a long time, the apparent randomness was treated as a kind of bedrock, an inexplicable feature of nature to be accepted but not understood, a brute fact about how the small-scale world behaves. But to accept randomness as a brute fact is to leave the central question unanswered, because everything depends on what that randomness really is. Is it a sign that the universe truly has not made up its mind about the future, a genuine fountain of novelty bubbling up at every measurement? Or is it an artifact of our limited perspective, a statistical shadow cast by a deeper, fully determined reality that we cannot see in full? The answer determines whether the frozen river is the true picture of time, or a beautiful approximation that breaks down at the smallest scales. And to make progress on that answer, we have to look more closely at the moment of measurement itself, at what it might mean for a blur of possibilities to become a single fact, and at the increasingly precise experiments that have begun to probe that moment directly, narrowing the space in which any explanation can hide. Because in recent years, the act of measurement has stopped being a vague philosophical placeholder and has become something physicists can manipulate, delay, reverse, and dissect in the laboratory. And what they have found has reopened the question of time's nature in ways that no one anticipated. The act of measurement, once treated as an untouchable boundary, where theory simply handed off to mystery, has in recent decades become an object of direct experimental investigation, and the results have steadily eroded the comfortable assumption that measurement is a simple, instantaneous event with an obvious meaning. To appreciate why this matters for the block universe, consider what the standard account asks us to believe. Before a measurement, a particle exists as a blur of possibilities, described by a mathematical object that captures every potential outcome and its likelihood. After the measurement, the particle has a single definite property, and all the other possibilities have vanished. The transition between these two states, the collapse, is where the randomness lives, and where the future, if it is open, would be getting written. So the obvious move, if you want to understand whether the future is genuinely open, is to study the collapse as closely as possible. What triggers it? How long does it take? Can it be interrupted, delayed, or undone? For most of the history of the theory, these questions were considered almost meaningless because measurement was treated as a primitive and unanalyzable act. But improvements in experimental control have made the collapse itself a target, and probing it has produced findings that complicate every simple story about time. One line of investigation concerns whether the choice of what to measure can be delayed until after the particle has seemingly already committed to a behavior. Recall the experiment in which particles pass through two openings and build up an interference pattern, the signature of each particle traveling as a wave through both openings at once. If, instead, you set up a detector to determine which single opening each particle actually passes through, the interference pattern disappears, and the particles behave like ordinary objects going through one opening or the other. The behavior depends on what you choose to measure. Detect the path, and you get particle-like behavior. Decline to detect the path, and you get wave-like behavior, the interference of possibilities. The natural assumption is that the particle decides how to behave when it reaches the openings, based on whether a path detector is present. But experiments have been devised in which the decision about whether to detect the path is delayed until after the particle has already passed through the apparatus, until it is, in some sense, too late for the particle to have known what kind of experiment it was entering. And the startling finding is that the outcome still matches the experimental arrangement, as though the particle's behavior at the openings were responsive to a choice made afterward. This is the kind of result that forces a confrontation with the meaning of time order in the physics of the small. On its face, it seems to suggest that a choice made now can influence what a particle did in the past, that the future arrangement of the experiment reaches back to shape the earlier behavior. That interpretation is dramatic, and it has to be handled with great care, because there are more conservative readings that avoid any literal backward influence. The careful conclusion most physicists draw is more subtle and in some ways more unsettling. It is that the particle never had a definite history in the first place, that there is no fact about which opening it went through, or whether it behaved as a wave or a particle, until the entire experiment, including the final choice of measurement, is complete. The past on this reading is not a fixed record that the present discovers. It is, in part, still indeterminate until the measurement that resolves it is made. The behavior at the openings was not decided, and then later revealed. It was never decided until the measurement settled it, and the measurement came afterward. Notice what this does to the simple opposition between a fixed past and an open future. The intuitive picture, the one the physics of the small seemed at first to support, was of a settled past, a special present, and an open future, with the present moment serving as the moving boundary where open possibility becomes fixed fact. But these delayed measurement experiments suggest that the past itself, or at least certain aspects of it, may not be fully fixed until later measurements pin them down. The boundary between determined and undetermined does not fall neatly between past and future, with the present as a clean dividing line. Instead, the determination of an event can depend on measurements made at times we would call later. The neat temporal ordering of becoming, in which reality crystallizes front to back, like ice forming on a river from upstream to downstream, does not survive contact with these results. The freezing, if it happens at all, does not respect the simple direction we expected. This is a remarkable development for the block universe debate because it cuts in an unexpected direction. The randomness and collapse of the physics of the small initially seemed to favor an open future against the frozen block. But the delayed measurement results suggest that the relationship between measurement and reality does not honor the clean temporal sequence that an open future requires. If a measurement now can be part of what determines an event that, by ordinary reckoning, already happened, then the present is not simply selecting outcomes from an open future while leaving a fixed past behind. The whole web of measurements and outcomes seems to be settled together in a way that does not privilege any particular moment as the site of becoming. And a reality that is settled all at once, without a moving boundary of becoming, looks far more like the timeless block than like the flowing river. The very experiments that seem to introduce genuine becoming, looked at more closely, may point back toward a structure in which all events, past and future, are determined together as a single, consistent whole. There is another related class of findings that deepens this picture concerning the reversibility of measurement. The standard story treats collapse as a one-way process, an irreversible event in which possibilities are lost forever, the blur replaced permanently by a single outcome. If that were strictly true, it would establish a clear arrow of time at the smallest scale, a genuine before and after marked by the irreversible destruction of possibilities, which would be a real point in favor of an open future and a flowing present. But careful experiments on very small, well-isolated systems have shown that what looks like collapse can sometimes be partial, and partial collapses can be reversed. By gently extracting only a little information about a system, and then carefully undoing that extraction, experimenters have been able to restore the original blur of possibilities, as though the partial measurement had never occurred. The possibilities that seem to be vanishing can be coaxed back. This suggests that collapse is not the sharp, irreversible, fundamental event the simple story makes it out to be. Under the right conditions, with sufficient isolation and control, the transition from blur to definite outcome can be slowed, partially performed, and even rewound. The implication is profound. If collapse can be reversed, then it is not a fundamental, irreversible act of becoming after all. It begins to look more like an ordinary physical process, one that can, in principle, run in either direction, governed by the same time-symmetric rules as the smooth evolution of possibilities. And if the apparent irreversibility of measurement in everyday situations is not fundamental but merely practical, a matter of information escaping into the environment in ways too complex to reverse, then the seeming arrow of time at the moment of measurement is not a basic feature of reality, but an emergent statistical effect, much like the way a shattered glass does not spontaneously reassemble, even though the underlying laws would permit it. The irreversibility we observe would be a consequence of complexity and scale, not a fundamental directionality built into the small-scale world. And once again, this points away from genuine becoming and back toward the timeless block, in which the apparent flow of time is an emergent feature of how large, complex information-leaking systems behave, rather than a fundamental fact about the universe. These experimental developments have not resolved the block universe debate, but they have transformed it. They have taken the measurement problem out of the realm of pure philosophy and made it a subject of laboratory manipulation. And in doing so, they have undermined some of the simplest arguments on both sides. The simple argument for an open future, based on the apparent randomness and irreversibility of measurement, is weakened by the discovery that measurement can be delayed, partially performed and reversed. Behaviors that do not fit a clean picture of possibility crystallizing into fact at a moving present. At the same time, the simple argument for the block universe, based on the smooth deterministic evolution of possibilities, has to contend with the stubborn fact that definite outcomes do occur, that measurements do yield single results, and that no one has fully explained why or how. The experiments have revealed a reality more intricate than either simple picture, one in which the relationship between time, measurement, and determination is genuinely strange, not in a theatrical sense, but in the precise sense that it does not match any of the intuitive frameworks we bring to it. What emerges from all of this is a growing suspicion among many physicists that the resolution will not come from choosing between the block universe and the flowing river as they are usually conceived. Both pictures may be importing assumptions about time that the deeper physics simply does not support. The block universe assumes that all events are determined together in a fixed structure, which fits the smooth evolution and the delayed measurement results, but struggles to explain why definite outcomes occur at all. The flowing river assumes a moving present, where becoming happens, which fits the occurrence of definite outcomes, but struggles against relativity and against the reversibility and delayability of measurement. The truth may require a framework in which the very notions of past, present, and future, of determination and becoming, are reconceived from the ground up. And several such frameworks have been proposed, each taking the puzzling experimental findings as a clue rather than an embarrassment, each trying to build a new picture of time that can accommodate both the timeless structure of relativity and the definite, probabilistic outcomes of the small-scale world. One of the most intriguing of these clues is the one we touched on, the hint that the future arrangement of an experiment seems relevant to what happens earlier. Taken at face value, this suggests something that physics has long resisted but never definitively ruled out: the possibility that influence can run backward in time, that the future can constrain the past just as the past constrains the future. For most of the history of science, this idea was dismissed as obviously absurd, a violation of the basic order of cause and effect. But the small-scale world has a way of forcing the reconsideration of ideas that seemed safely buried, and a growing number of researchers have begun to take seriously the possibility that the apparent randomness of measurement and the strange role of later choices in determining earlier events might be explained by allowing the future to play a role in the present. If they are right, it would not merely tweak the block universe. It would transform the entire question of time's nature, replacing both the frozen river and the flowing river with something stranger and, to its advocates, more complete. And it would do so by taking one of the most firmly held assumptions in all of physics, the assumption that causes always precede their effects, and asking whether it might at the deepest level be false. The assumption that causes always precede their effects is so deeply embedded in human thought that questioning it feels almost like questioning logic itself. We strike the match, and then it lights, never the reverse. We make the decision, and then the consequences follow. The entire structure of planning, regret, responsibility, and learning depends on the past shaping the future, and never the other way around. And yet, when physicists examine their most fundamental equations, they find something that ought to give them pause. The basic laws governing matter and energy at the smallest scales, like the laws of relativity, do not contain any built-in direction of time. They work equally well, run forward or backward. If you filmed the interaction of two particles and played the film in reverse, the reversed process would also be a perfectly valid solution of the equations, equally consistent with the laws of physics. The fundamental laws, in other words, are time symmetric. They do not distinguish past from future. The arrow of time, the obvious fact that the world unfolds in one direction and not the other, does not appear in the basic equations at all. It has to come from somewhere else. This time, symmetry of the fundamental laws is the opening through which the idea of backward causation enters. If the laws themselves do not prefer one direction of time, then there is no fundamental reason drawn from the laws why influences should only travel from past to future. The restriction that causes precede effects might not be a law of nature at all, but a feature of the particular circumstances we happen to inhabit, much as the one-way melting of ice or shattering of glass reflects not the underlying laws, but the statistical behavior of large numbers of particles. And if the prohibition on backward influence is not fundamental, then perhaps at the level of individual particles and measurements, where the statistics of large numbers do not yet wash everything into a single direction, influences really can run both ways. Perhaps the future really can reach back and shape the past, at least in the subtle, hidden manner that the small-scale world permits. This idea that the future can influence the present and the past is called retrocausality, and it has been proposed in various forms as a solution to some of the deepest puzzles of the small-scale world. Its appeal is best understood by recalling the central mystery, the apparent randomness, and the role of measurement choices in determining outcomes. The standard picture says that a particle exists as a blur of possibilities, and that when measured, it randomly collapses to a single outcome, with the choice of outcome determined by nothing at all. A genuine roll of cosmic dice. This is deeply unsatisfying to many physicists because it abandons the principle that has guided science from the beginning, the principle that everything that happens has a reason, that effects have causes. Pure randomness is the absence of explanation, a place where the chain of causes simply stops. Retrocausality offers a way to restore the chain. What if the outcome of a measurement is not random at all, but is determined in part by the future, by the very measurement that will be performed and the arrangement of the apparatus that will do the measuring? Then the seeming randomness would not be a fundamental gap in explanation, but a consequence of our inability to see the future influences that are shaping the present. The particle's behavior would be determined by both its past and its future, by the conditions at both ends of its journey, and the appearance of randomness would arise because we know only the past conditions and remain blind to the future ones. This reframing dissolves several of the most troubling features of the small-scale world in a single stroke. The delayed measurement results, in which a later choice seems to determine an earlier behavior, are no longer paradoxical. They are exactly what one would expect if the future measurement genuinely is one of the factors determining the earlier behavior. The particle behaved as it did at the openings because of conditions at both ends. The source that emitted it and the detector that would eventually receive it, and the later choice of detector was simply part of the full set of conditions all along. There is no spooky reaching back through time in the sense of a signal traveling into the past, no message sent backward. Rather, the entire history of the particle, from emission to detection, is determined as a consistent whole by the conditions at both temporal ends, in the same way that a stretched string between two fixed points takes on a shape determined by both ends at once, not by one end imposing itself on the other. The future and the past constrain the present together, and the present is the consistent solution that satisfies both sets of constraints. This way of thinking has a natural and striking relationship to the block universe, one that deserves careful attention because it represents a genuine shift in the terms of the debate. At first glance, retrocausality might seem to be a way of escaping the frozen block, of restoring some kind of dynamism and openness. But on closer inspection, it does something more interesting. It actually fits very comfortably within a block universe, while transforming what the block universe means. If the future can influence the past, then the future must, in some sense, already be there to do the influencing. An open, not yet existent future cannot reach back and constrain anything, because there's nothing there to do the constraining. For the future to play a role in determining present outcomes, the future events must have the same kind of reality as past events. They must be part of the fixed structure. So retrocausality, far from breaking the block, presupposes it. It requires the four-dimensional structure to be present as a whole, with both temporal ends real and capable of imposing constraints on what lies between them. But the block universe that emerges from retrocausality is not quite the same as the one that emerged from relativity alone. The relativistic block was a static, given structure, simply there, with no particular logic to how its contents were arranged beyond the requirement of consistency with the laws. The retrocausal block is more like a structure that settles into a self-consistent configuration under constraints applied from both temporal directions. It is determined not by the past pushing forward moment by moment, but by the whole pattern of conditions, past and future, settling together into the unique arrangement that satisfies all of them at once. This is sometimes described as a kind of global consistency, in which the universe is not computed forward from initial conditions like a film being generated frame by frame, but is rather the complete solution to a vast set of mutual constraints, a pattern that fits together as a coherent whole across all of time. The block is still timeless, still complete, still containing all moments equally, but the principle that determines its contents is no longer the one-way march of cause and effect from past to future. It is a two-way, all-at-once consistency that does not privilege any temporal direction. There is a particular model built on these ideas that has attracted considerable attention, because it offers a concrete mechanism for how two-way influence might work at the level of individual measurements. The model imagines that when a particle is emitted, it sends out not only an ordinary wave traveling forward in time toward the future, but also a partner wave traveling backward in time toward the past. The forward wave carries the influence of the emission toward the eventual detection in the normal way. The backward wave carries the influence of the detection back toward the emission. The two waves meet, overlap, and through their interaction establish a kind of agreement, a confirmed transaction between the emission event and the detection event, settling the properties of the particle in a way that satisfies both ends. The particle in this picture is not a thing that travels from past to future, accumulating a definite history as it goes. It is the established connection between an emission and a detection, a handshake across time, agreed upon by influences traveling in both directions and existing as a completed whole rather than as an unfolding process. The appeal of this kind of model is that it offers an explanation for the otherwise inexplicable. The apparent randomness of which detector receives the particle, of where exactly it lands, becomes a consequence of which transactions successfully complete, which handshakes are confirmed, given the conditions at both ends. The probabilities that the standard theory simply asserts, without explanation, emerge naturally from the structure of these two-way connections. The role of the measurement, so mysterious in the standard account, becomes clear because the measurement is one of the two ends that must agree for a transaction to occur. The collapse from blur to definite outcome is not a mysterious physical event happening at a special moment, but the establishment of a completed connection spanning the full duration between emission and detection, a connection that exists timelessly within the block once all the constraints are satisfied. and the delayed measurement puzzles dissolve, because in a transaction spanning the full time between emission and detection, there is no question of the particle deciding what to do at the openings before knowing what kind of measurement awaits. The whole transaction, including the measurement, is settled together. These ideas remain contested, and it is important to be clear that retrocausal models are not the accepted standard view, but rather a serious minority program, pursued by a community of physicists and philosophers who find the standard account's reliance on unexplained randomness and unexplained collapse unsatisfying. The models face genuine challenges, making them fully precise, ensuring they reproduce all the established predictions of the standard theory, and ruling out the paradoxes that backward causation seems to invite, such as the possibility of sending signals into the past to alter events in self-contradictory ways, requires great care. The usual response to the paradox worry is that the backward influences are hidden, statistical, and constrained by the requirement of global consistency in such a way that they can never be used to send a controllable signal into the past or to create a genuine contradiction. The future influences the past only in ways that, when everything is added up, remain consistent and never allow the kind of paradox that would let you change what has already definitely happened. The constraints are subtle, the influences are not freely manipulable, and the result is a universe that hangs together as a consistent whole without ever permitting the logical impossibilities that naive backward causation would seem to allow. What makes this entire line of thought so significant for the question we are pursuing is that it offers a genuinely new way to think about the block universe, one that may dissolve the original tension rather than simply taking a side in it. The original conflict was between relativity, which seemed to demand a timeless block, and the small-scale world, which seemed to demand an open future through its apparent randomness and becoming. Retrocausality suggests that this conflict rested on a misunderstanding of the randomness. The randomness was never a sign of an open future at all. It was a sign that the future was influencing the present in ways we could not see, that the universe was being determined from both ends at once. Properly understood, the apparent randomness is fully compatible with, and even points toward, a block universe, but a richer block than relativity alone suggested, one whose contents are fixed by global consistency across all of time, rather than by the forward march of cause and effect. The frozen river is real, but it was never frozen from upstream to downstream. It was frozen all at once, the entire course settling into the only shape consistent with the conditions at both the source and the sea. And if this is right, then the deepest puzzles of the small-scale world are not evidence against the block universe, but clues to its true structure, signs of the two-way logic by which a timeless universe arranges its contents into a single self-consistent whole. But not everyone accepts that the randomness should be explained away, and the most successful and widely discussed response to the measurement problem takes the opposite approach entirely. Rather than restoring determinism by appealing to hidden future influences, it restores determinism by denying that collapse ever happens at all, and in doing so, it proposes a picture of reality so vast and so strange that it makes even the block universe seem modest by comparison. It accepts the smooth, deterministic evolution of possibilities as the complete and literal truth, and it asks what follows if nothing is ever lost, if every possibility that the equations describe is fully real. The answer it arrives at reshapes not only our understanding of time, but our understanding of how many worlds there are. The approach that denies collapse ever happens begins from a position of stark simplicity, almost austerity. The smooth evolution of possibilities, the part of the theory described precisely by equations, is deterministic and contains no randomness and no collapse. So why not take that evolution as the complete and literal truth, the whole of reality, with nothing added? Why introduce a mysterious, unexplained collapse at all, when the equations work perfectly well without one? The standard account inserts collapse to explain why we observe single, definite outcomes, rather than blurs of possibility. But what if we do not need to explain away the blur? Because the blur is real, and the appearance of single outcomes is explained in a completely different way. This is the move at the heart of the interpretation, and its consequences are staggering. If the blur of possibilities never collapses, if every possibility described by the equations continues to evolve and remains fully real, then all the outcomes that the standard theory says are randomly selected among actually happen. Every one of them, the measurement that seems to yield a single random result, in fact yields all possible results, each in its own branch of a constantly dividing reality. To make this concrete, return to the particle and the screen. The standard account says the particle exists as a blur of possible landing positions, and, when it strikes the screen, randomly lands at one spot, the other possibilities vanishing. The no-collapse interpretation says something entirely different. It says the particle lands at every possible spot, but each landing occurs in a separate branch of reality. In one branch, the experimenter sees the particle land here. In another branch, an equally real experimenter sees it land there. In yet another, somewhere else. There is no single outcome, because there is no collapse to produce one. Instead, reality itself splits, branching into as many versions as there are possible outcomes, with a copy of the experimenter in each branch, each copy convinced that they have witnessed a single definite result, each unaware of the others. The randomness we experience is not randomness in the universe. It is the consequence of each version of us finding ourselves in one particular branch, unable to perceive the others, mistaking our particular branch for the whole of reality. This interpretation, in which reality continuously branches into countless versions, each containing its own copies of observers experiencing their own definite outcomes, is among the most discussed responses to the measurement problem, and it has a powerful logical appeal precisely because of what it removes. It removes the collapse, the one piece of the standard theory that no equation describes and that no one can explain. It removes the randomness, replacing it with a fully deterministic evolution in which nothing is left to chance, because everything that can happen does happen. It removes the special role of measurement, treating measurement as just another physical interaction, no different in kind from any other, that causes the branching observer to become correlated with the various outcomes, and thereby to split along with them. What it adds in exchange for these removals is an almost unimaginable proliferation of reality, a constant branching into more and more versions of the universe, each as real as any other, the total number growing without limit as every interaction everywhere multiplies the branches. For our question about the nature of time, this interpretation has a particularly important feature. It is fully deterministic and, like relativity, it is naturally at home in a block universe, though a block of extraordinary richness. Because nothing is ever randomly selected, because the evolution is smooth and lawful throughout. The entire branching structure can be regarded as a single, fixed, four-dimensional object, or rather a vastly higher dimensional object, containing all the branches at once. There is no genuine becoming, no moment when an open possibility is resolved into a fixed fact, because no possibility is ever eliminated. All of them are realized, all of them coexist, and the whole structure simply is, complete and timeless, exactly as the block universe requires. The flow of time, the sense of moving from an open future into a fixed past, is once again an illusion produced by the perspective of observers embedded within the structure. Each version of an observer experiences a definite sequence of outcomes, a particular path through the branching tree, and mistakes that path for the unfolding of a singular reality. But the tree as a whole does not unfold. It is there in its entirety, every branch coexisting, the grandest possible version of the frozen river, in which not one river, but an unfathomable multitude of rivers, branching and rebranching, all exist together in a single timeless structure. This is a remarkable convergence. The relativistic argument led to a block universe through the relativity of simultaneity. The no-collapse interpretation leads to a block universe through the denial of collapse and the reality of all branches. Two completely different routes, one from the physics of the very large and fast, the other from the physics of the very small, arrive at the same destination, a timeless structure containing all events, with no genuine flow and no privileged present. For advocates of the block universe, this convergence is powerful evidence. When independent lines of reasoning, starting from different domains and different principles, point toward the same conclusion, that conclusion gains credibility. Both of our most fundamental theories, properly interpreted, seem to describe a universe without genuine temporal becoming, a universe that simply exists in its entirety, rather than coming into being moment by moment. And yet, the no-collapse interpretation comes at a price that many find too high to pay, and the nature of that price is worth examining, because it reveals something important about the limits of these arguments. To accept this interpretation is to accept that reality contains an essentially infinite number of branches, that there are countless versions of every person, every planet, every event, that everything which can happen does happen somewhere in the branching structure, and that the singular world we seem to inhabit is a vanishingly small slice of a reality, almost beyond comprehension in its vastness. Some find this extravagant beyond reason, a violation of the principle that we should not multiply entities beyond necessity. Why accept an infinity of unobservable worlds simply to avoid the awkwardness of an unexplained collapse? Others respond that the extravagance is only in the number of worlds, not in the principles, and that the interpretation is actually the simplest possible, because it adds nothing to the bare equations and merely takes them literally. The dispute over whether this interpretation is the most economical or the most extravagant of all possibilities is itself one of the liveliest in the philosophy of physics, and it has no clear resolution because it turns on what kind of simplicity we value, simplicity of principle or simplicity of contents. There are also genuine technical difficulties that prevent the no-collapse interpretation from being a clean and decisive solution. The most pressing concerns the probabilities. The standard theory does not merely say that various outcomes can happen. It assigns precise probabilities to them, and those probabilities are confirmed with extraordinary accuracy by experiment. Some outcomes are common, others rare, in exact proportions the theory specifies. But if every outcome actually happens, in its own equally real branch, then in what sense can one outcome be more probable than another? Every outcome occurs with certainty in its own branch. The notion of probability seems to lose its meaning when all possibilities are realized. Advocates of the interpretation have developed sophisticated arguments to recover the probabilities, to explain why an observer should expect to find themselves in the more probable branches more often, why the rare outcomes should be experienced as rare, even though they definitely happen somewhere. These arguments are subtle and contested, drawing on ideas about rational expectation and the weighting of branches, and whether they succeed is a matter of ongoing debate. The interpretation's elegant removal of collapse and randomness is purchased at the cost of a real difficulty in recovering the very probabilities that make the theory testable in the first place. For the question of time, however, the technical difficulties with probability do not change the central point. Whether or not the probabilities can be fully recovered, the no-collapse interpretation, if accepted, lands squarely in the block universe camp. It describes a timeless, deterministic, all-encompassing structure in which every possibility is real and nothing genuinely comes into being. So we now have two of the leading approaches to the measurement problem, retro-causality and the no-collapse interpretation, both pointing toward a block universe, though they arrive there by very different paths and paint very different pictures of what the block contains. The retrocausal block is a single self-consistent world, its contents fixed by constraints from both temporal directions. The no-collapse block is an endlessly branching multitude of worlds, all coexisting in a structure of unimaginable richness. Both deny genuine becoming. Both make the flow of time an artifact of perspective. Both reinforce, from the side of the small-scale world, the conclusion that relativity already suggested from the side of the large. This might seem to settle the matter overwhelmingly in favor of the block universe. The two great pillars of physics and the leading interpretations of the more puzzling one all converge on timelessness. But it is precisely here that we must be most careful, because the convergence, impressive as it is, conceals a crucial fact. These are interpretations, not measurements. The no-collapse interpretation and the retrocausal interpretation make, for the most part, exactly the same experimental predictions as the standard account and as each other. They agree on what the instruments will read. They disagree only on what is really happening behind the readings, on the underlying nature of reality that produces the same observable results. No experiment performed to date can distinguish between a universe that branches endlessly, a universe constrained from both temporal ends, and a universe in which collapse genuinely happens at a flowing present. They are, as far as observation can tell, equivalent. The choice between them is made on grounds of elegance, economy, and philosophical preference, not on grounds of measurement. And this means that the convergence toward the block universe, however suggestive, is a convergence of interpretations, of ways of reading the same data, not a convergence of forced experimental conclusions. This is the sobering reality at the heart of the entire subject. The block universe is supported by powerful arguments from both relativity and the small-scale world. But every one of those arguments, examined closely, rests at some crucial juncture on an interpretive choice, on a decision about what the mathematics means, that the mathematics itself does not compel. Relativity establishes the relativity of simultaneity, but not the reality of the future. The small-scale world establishes definite outcomes and precise probabilities, but not whether those outcomes involve genuine becoming or merely the appearance of it. The interpretations fill the gaps, and they fill them in ways that favor the block. But the gaps are real, and other ways of filling them remain possible. This is why the block universe, after more than a century, remains a hypothesis rather than an established fact. Why it is debated rather than simply accepted. The case for it is strong, but not decisive, suggestive, but not conclusive, resting on a foundation of confirmed physics overlaid with unconfirmed, perhaps unconfirmable, interpretation. And so, the natural next question becomes unavoidable. If the choice between a timeless block and a flowing present cannot be settled by the experiments we have, is there any prospect of new physics that could settle it? Is there some deeper theory, some not yet completed framework, in which the question of whether time genuinely flows would no longer be a matter of interpretation, but a matter of fact, decided by the structure of the theory itself? Many physicists believe there is, and they believe it lies in the direction of the great unfinished project of theoretical physics, the attempt to unite relativity and the small-scale world into a single coherent framework. For in that union, the nature of time is not a peripheral question, but the central obstacle, the very thing that makes the two theories so hard to reconcile. And some of the most provocative proposals to emerge from that effort suggest that the resolution will be stranger than either the block or the river. That time, as we conceive it, whether flowing or frozen, may not be a fundamental feature of reality at all, but something that emerges from a deeper level where time, in any familiar sense, simply does not exist. The great unfinished project of theoretical physics is the unification of relativity, which governs gravity and the large-scale structure of space-time, with the physics of the small-scale world, which governs matter and energy at the level of particles. Each theory is magnificently successful in its own domain, and each has passed every experimental test put to it. But they are built on incompatible foundations, and nowhere is the incompatibility sharper than in their treatment of time. Relativity treats time as a flexible dimension, woven together with space into a smooth, continuous fabric that can stretch, curve, and tilt, with no preferred present and no universal clock. The small-scale world, in its standard formulation, treats time quite differently, as a fixed background parameter against which the blur of possibilities evolves, an external clock ticking uniformly while quantum systems do their probabilistic dance. These two conceptions of time cannot both be exactly right, and the effort to combine the theories into a single framework of quantum gravity has repeatedly run aground on precisely this conflict. The nature of time is not a side issue in the search for unification. It is the central obstacle, the knot that must be untied before the two theories can be joined. The difficulty becomes acute when physicists try to apply the methods of the small-scale world to gravity and space-time themselves. In relativity, space-time is not a passive stage, but an active participant, bending in response to matter and energy, its geometry determined by what it contains. To bring this dynamic space-time into the framework of the small-scale world, one would need to describe the geometry of space-time itself as a blur of possibilities, a superposition of different shapes, evolving in time. But here, a strange thing happens. When the equations of relativity are recast in the form required for this kind of treatment, time disappears. The central equation that emerges the equation meant to govern the quantum state of the entire universe, including its space-time geometry, contains no time variable at all. It describes a structure that simply is, without any reference to evolution, without any before and after, without any ticking clock. The universe, at this most fundamental level, appears to be static, timeless, frozen in a way that goes beyond even the block universe. Because in the block universe, at least time exists as a dimension, whereas here, time seems to vanish entirely from the fundamental description. This result, the apparent disappearance of time from the fundamental equation of quantum gravity, is known as the problem of time, and it is one of the deepest and most disorienting puzzles in all of theoretical physics. It seems to say that at the most basic level of reality, there is no time, no change, no evolution, just a single timeless quantum state of everything. And this immediately raises a question that borders on the absurd. If the fundamental description of the universe contains no time, why do we experience time so vividly? Why does anything seem to happen? Why is there change, motion, the relentless sense of one moment following another, if the deepest layer of reality is utterly static? The problem of time is not merely a technical difficulty in solving certain equations. It is a challenge to the very idea that time is a fundamental feature of the universe. And the leading response to it suggests something that transforms the entire block universe debate. It suggests that time is not fundamental at all, that it does not exist at the deepest level, but emerges somehow from the timeless structure beneath, in the way that temperature emerges from the motion of molecules that individually have no temperature. To grasp how time might emerge from timelessness, consider an analogy drawn from the way the small-scale world handles correlations between different parts of a system. In the timeless quantum state of the universe, different parts can be correlated with one another, their properties linked, so that the condition of one part carries information about the condition of another. Now imagine that one part of the universe functions as a clock, a system whose configuration changes in a regular, ordered way, like the position of a hand on a dial. And imagine that the rest of the universe is correlated with this clock, so that for each configuration of the clock, the rest of the universe has a corresponding configuration. Then, although the total state is timeless, containing no time variable, an observer who is part of the universe and who reads the clock would experience time. They would find that when the clock reads one value, the rest of the universe is in one configuration, and when the clock reads another value, the rest of the universe is in another, and they would interpret this correlation as the passage of time, as the universe changing from one moment to the next. But there would be no actual change in the timeless total state. The appearance of time would arise entirely from the correlations within a static structure, from the way different configurations of the universe are linked to different configurations of the clock. This is a profound reconceptualization of what time is. On this view, time is not a fundamental dimension along which the universe evolves. It is a relationship, a pattern of correlation between a clock subsystem and the rest of the universe, encoded within a fundamentally timeless state. Change is not something that happens to the universe as a whole. It is something that appears within the universe when one part is read as a clock against which the configurations of other parts are compared. The universe does not unfold in time. Rather, time is the name we give to a certain structure of relationships within a static whole. The way that different configurations are correlated with the readings of whatever serves as a clock. And remarkably, this idea has received a measure of experimental support. In carefully constructed laboratory systems, researchers have been able to create small, isolated setups in which one part serves as a clock and another part is correlated with it, and they have shown that an observer who could only access the correlation between the two parts without any external time reference would perceive the second part as evolving in time, even though the total system, viewed from outside, remains in a fixed, unchanging state. Time, in these miniature model universes, genuinely emerges from a timeless whole, exactly as the theoretical idea predicts. The implications of emergent time for the block universe debate are subtle and far-reaching, and they deserve careful unpacking, because they do not simply confirm or refute the frozen river, they reframe the entire question. The block universe, as it arose from relativity, was a four-dimensional structure in which time was a real dimension, one of the axes of the structure, even if it did not flow. The emergent time idea goes deeper. It suggests that even this dimensional time is not fundamental, that beneath the four-dimensional block lies a more basic, timeless quantum reality from which the appearance of a time dimension and the appearance of its flow both emerge as features of correlation and perspective. The block universe, on this view, is not the bottom layer of reality, but an intermediate layer, a useful approximation that emerges from something more fundamental and stranger, a reality in which time in any form, whether flowing or merely dimensional, is not present at all. The frozen river is itself an emergent phenomenon, a pattern that appears at a certain level of description but dissolves when one looks deeper. This might seem to settle the original debate decisively in favor of timelessness, and in one sense it does, because it pushes the absence of fundamental flow even further than the block universe did, denying that time is even a basic dimension of reality. But in another sense, it reopens the question in a new form, because it suggests that the entire framing of the debate, block versus flow, may have been built on a mistaken premise, the premise that time is a fundamental thing whose nature, whether static or dynamic, we were trying to determine. If time is emergent, then asking whether the fundamental reality is a frozen block or a flowing river is like asking whether the fundamental reality is hot or cold, when temperature itself is not a fundamental property, but emerges from underlying motion. The question may simply not apply at the deepest level. Time, with all its puzzles of flow and becoming and the reality of past and future, would be a feature of the emergent description, the level at which clocks and observers and correlations exist, and the deeper reality would be neither frozen nor flowing, but something to which the very concept of time does not apply. There is something both clarifying and vertiginous about this resolution. It clarifies because it explains why the block versus flow debate proved so intractable. Both sides were assuming that time was fundamental and arguing about its nature, when in fact time may be emergent, and the disagreement may have been a category error, an attempt to apply concepts at a level where they do not belong. It is vertiginous because it removes the ground entirely, suggesting that the reality we inhabit, with its vivid flow of time, its definite past, and open seeming future, is a kind of surface phenomenon floating atop a timeless deep, a structure of correlations within an eternal, changeless whole. The river is not just frozen. The river, as a fundamental feature of reality, does not exist at all. What exists is a timeless quantum state, and the river is what that state looks like from the inside, to a subsystem that reads another subsystem as a clock, and thereby experiences the illusion of flow. Of course, quantum gravity remains an unfinished theory, and the emergent time idea, however suggestive, is not established physics. The fundamental equation that lacks a time variable is one approach to quantum gravity among several, and its interpretation is contested. The laboratory demonstrations of emergent time use small model systems, carefully engineered analogies, not the actual quantum state of the universe, and extrapolating from these models to reality as a whole is a substantial leap. The mathematics of how a smooth, four-dimensional spacetime, with all its relativistic structure, emerges from a timeless quantum substrate is far from fully worked out. There are competing approaches to quantum gravity that treat time differently, some of which try to preserve a more fundamental role for time, and the field has not converged on a single answer. So while the emergent time idea is one of the most intriguing developments to bear on the block universe question, it is a frontier of active research, not a settled conclusion. It points toward a possible resolution, but the resolution is not yet in hand. What the emergent time idea does establish, even in its unfinished state, is that the deepest physics we have does not obviously support the intuitive picture of a flowing present, and may not even support the dimensional time of the block universe, but instead points towards something more radical, a fundamental timelessness from which time in all its forms emerges. This is a powerful consideration because it means that the burden of proof has shifted. The intuition that time flows, that the present is special, that the future is open, finds no foothold in relativity, struggles to establish itself through the interpretations of the small-scale world, and seems to evaporate entirely at the level of quantum gravity. At every level of our deepest physics, the trend is the same: away from flow and toward structure, away from a dynamic present and toward a timeless whole. The flowing river has been retreating before the advance of physics for over a century, and the latest developments push it back further still, into the realm of emergent appearance rather than fundamental reality. And yet the river has not surrendered, and the reasons it persists are not merely stubbornness or sentiment. There remain serious thinkers who argue that the relentless trend toward timelessness reflects a limitation of our current physics rather than a truth about reality, that the disappearance of time from our equations is a sign that something is missing, not that time is unreal. They point out that physics, by its very method, tends to describe the world in terms of timeless mathematical structures, equations, and geometries that capture patterns without capturing the flow, and that this methodological preference may be blinding us to the genuine reality of temporal passage, which by its nature may be exactly the kind of thing that a timeless equation cannot capture. The absence of flow in our theories on this view is a feature of how we do physics, not a discovery about the world. And there is a recent body of work, both theoretical and at the edges of the experimental, that takes this concern seriously and attempts to find a place for genuine temporal becoming within fundamental physics, to build the flow back into the foundations rather than dismissing it as emergent illusion. It is to this work, the most direct recent attempt to confront the block universe on its own terms, that we now turn. The recent work that takes temporal becoming seriously begins from a critique of the very method by which physics has reached its timeless conclusions. The argument runs as follows. Physics describes the world using mathematics, and the kind of mathematics it favors, equations relating quantities, geometric structures representing spacetime, captures the world as a static set of relationships. When you write down an equation describing how a system evolves, you produce a timeless mathematical object, a curve or a surface or a formula, that represents the entire history of the system all at once, laid out for inspection. The equation does not flow. It sits on the page, complete. And because physics represents the world this way, it naturally arrives at the conclusion that the world itself is a timeless structure, because that is what its representations are. But this, the critics argue, may be a confusion of the map with the territory. The fact that our mathematical representations are timeless does not mean that what they represent is timeless. A photograph of a waterfall is motionless, but the waterfall is not. By insisting on timeless mathematical descriptions, physics may have built the conclusion of timelessness into its methods from the start, guaranteeing that it would find a block universe simply because a block is the only kind of thing its equations can describe. This critique opens the door to a different research program, one that asks whether physics can be reformulated to include genuine temporal becoming as a fundamental feature, rather than treating time as either a static dimension or an emergent illusion. The proponents of this program argue that the flow of time, the coming into being of new events, the genuine openness of the future, are not illusions to be explained away, but fundamental facts to be incorporated into the foundations of physics. They take the vivid human experience of temporal passage not as a perceptual error, but as direct evidence of a real feature of the universe, a feature that our current theories, with their timeless mathematics, have systematically failed to capture. And they have begun to construct frameworks in which the laws of physics themselves are allowed to be dynamic, in which the future is genuinely open and only the past and present are real, in which the universe is not a finished block, but a growing structure, accumulating new moments as time passes. One version of this approach revives and refines an older idea, the growing block universe, which occupies a middle ground between the frozen block and the flowing river. The growing block agrees with the frozen block that the past is real, fixed, and unchangeable, a settled structure of events that have definitely happened. But it disagrees about the future. In the growing block, the future is not real. It does not yet exist. Reality consists only of the past and the present, a four-dimensional structure that grows as time passes, accumulating new layers of events at its leading edge, the present moment, which is the boundary where new reality is continually added. The present is special in this picture, not because it is the only moment that is real, as the flowing river holds, but because it is the growing edge, the frontier where the not yet existent becomes existent and joins the fixed structure of the past. Time genuinely passes, in the sense that the structure genuinely grows, new events genuinely come into being, and the total content of reality genuinely increases. But the past, once it has come into being, remains permanently real, exactly as the block universe insists. The growing block has real attractions, because it tries to honor both the physics and the intuition. It honors the intuition that the future is open and that time genuinely passes, by making the future unreal and the growth of reality a fundamental fact. It honors the physics by accepting that the past is a fixed four-dimensional structure, consistent with relativity's description of past events. And it offers a natural account of why the present feels special. Because the present really is special, the unique growing edge of reality. For these reasons, it has attracted serious philosophical defense as a way to reconcile the timeless tendencies of physics with the dynamic character of experience. But it faces a severe difficulty, the same difficulty that haunts every attempt to introduce a special present into a relativistic universe. Relativity, as we have seen, denies that there is any universal present, any objective now that is the same for all observers. But the growing block requires exactly such a universal present, a single objective leading edge where reality is being added, the same for everyone. If different observers have different presents, sliced at different angles, then they have different leading edges, and reality would be growing along many different fronts at once, in contradictory ways, with events that are real for one observer, not yet real for another. The growing block seems to demand the very universal present that relativity forbids, and reconciling the two has proven extremely difficult. The most recent and ambitious attempts to defend a dynamic universe try to address this difficulty head-on, and they do so in ways that genuinely engage with the deepest physics rather than ignoring it. One strategy is to argue that relativity, despite appearances, does not actually rule out a preferred present, but merely fails to detect one. On this view, there really is an objective universal now, a true leading edge of becoming, but it is hidden from our measurements because the effects that would reveal it are masked by the very symmetries of relativity. The preferred present exists, but it is screened from observation, leaving the relativistic description with its relative simultaneity as an accurate account of what we can measure, while not being the complete account of what is real. This is a coherent position, and it cannot be ruled out by experiment, precisely because the preferred present is, by hypothesis, undetectable. But it pays a heavy price, the same price noted earlier, of postulating something real that plays no role in any measurement and leaves no trace in any equation. An article of metaphysical faith adopted to preserve the reality of temporal passage against the timeless tendencies of physics. A more radical strategy abandons the attempt to fit becoming into the existing framework of relativity, and instead proposes that the framework itself must change, that a deeper theory will reveal a preferred structure of time that relativity only approximates. The proponents of this view point to the unfinished state of quantum gravity and argue that the final theory, when it is completed, may well restore a fundamental role for time, may reveal that the smooth relativistic spacetime, with its relativity of simultaneity, is itself an approximation that emerges from a deeper level where time does have a preferred direction and a genuine flow. They note that some approaches to quantum gravity do introduce a preferred slicing of space-time, a fundamental notion of simultaneity that relativity lacks, and they suggest that this preferred slicing could be the objective present that the growing block requires, hidden at the relativistic level, but real at the deeper one. On this view, the disappearance of time from the fundamental equation of quantum gravity. The problem of time is not evidence that time is unreal, but a symptom of using the wrong framework, a sign that the standard approach to quantum gravity has made a wrong turn precisely by trying to apply the timeless methods of the small-scale world to gravity. A different approach, one that takes time as fundamental from the start, might avoid the problem of time altogether and deliver a theory in which becoming is real and the future is genuinely open. This is where the most recent theoretical work becomes genuinely provocative, because some physicists have begun to construct exactly such theories, frameworks in which the laws themselves evolve, in which the future is open not just for the contents of the universe, but for the laws governing it, in which the universe is a fundamentally dynamic, creative process, rather than the unfolding of a predetermined structure. In these frameworks, the block universe is rejected at the deepest level. There is no fixed four-dimensional structure containing all events. There is only the present, continually generating the next moment, according to laws that may themselves be changing, with the past preserved as a fixed record, and the future genuinely non-existent until it is created. These theories are speculative, and they face enormous challenges in reproducing the well-established successes of relativity and the small-scale world, which are, after all, beautifully described by the timeless mathematics these new approaches seek to replace. But they represent a serious intellectual effort to take the reality of time seriously, to build physics around becoming rather than around static structure, and to challenge the century-long drift toward timelessness at its foundations. What can be said about the prospects of this effort? It is, at present, very much a minority program, swimming against the powerful current of evidence and interpretation that flows toward the block universe, the convergence of relativity, the leading interpretations of the small-scale world, and the emergent time idea of quantum gravity all point away from fundamental becoming and toward a timeless structure. To defend genuine temporal passage, one must either postulate an undetectable preferred present, accepting the cost of unobservable metaphysics, or bet on a future revolution in physics that will overturn the relativistic and quantum frameworks at their foundations and restore time to a fundamental role. Neither option is comfortable, and neither is supported by current experiment. But neither is refuted by current experiment either, and that is the crucial point. The block universe, for all its support, has never been experimentally confirmed against the dynamic alternatives, because the crucial question, whether the future already exists, lies beyond the reach of measurement. The dynamic universe remains a live possibility, kept alive not by evidence in its favor, but by the absence of decisive evidence against it, and by the persistent, powerful intuition that time genuinely passes, an intuition that its defenders refuse to dismiss as mere illusion. This brings us to the threshold of the most recent developments, the work that some have claimed amounts to a genuine solution to the block universe problem, a way of finally deciding between the frozen structure and the dynamic alternatives. The claims are bold, and they come from several directions at once. From new theoretical frameworks that purport to derive the arrow of time from deeper principles, from new experiments that probe the relationship between time and the small-scale world with unprecedented precision, and from new mathematical approaches that attempt to capture becoming within rigorous physics. Whether any of these claims holds up, whether the block universe has truly been solved or merely reframed once again, is the question we must now confront directly. For the convergence toward timelessness, however impressive, has always rested on interpretation rather than measurement, and any genuine solution would have to break that pattern, to offer something that decides the question rather than merely interpreting the same ambiguous data in one more way. The decisive test, if it exists, would have to find an observable difference between a universe that flows and a universe that simply is, And it is precisely such a difference that the newest work claims, controversially, to have found. The newest work that claims to bear decisively on the block universe comes from a recognition that the entire century-long debate has suffered from a single structural weakness, namely that the competing pictures of time made no different predictions about anything observable. A frozen block and a flowing river, a growing block and an endlessly branching multitude, all agreed perfectly on what every instrument would read. They disagreed only about the underlying reality behind the readings, and disagreements of that kind, by their nature, cannot be settled by experiment. So the most promising recent approaches have focused precisely on breaking this symmetry, on finding some respect in which a universe with genuine temporal becoming would behave differently from a timeless block, some observable consequence that would distinguish flow from structure. If such a difference could be identified and measured, the debate would shift from interpretation to evidence, and the question of whether time genuinely passes would become, for the first time, an empirical question with a definite answer. One line of this work focuses on the arrow of time and its relationship to the second law of thermodynamics, the principle that disorder, measured by a quantity called entropy, tends to increase. The increase of entropy is the most familiar physical manifestation of time's direction. Heat flows from hot to cold, never the reverse. Structures decay, mix, and disperse, never spontaneously assembling. A drop of ink spreads through water, but never gathers itself back into a drop. This one-way behavior, ubiquitous and unmistakable, is the clearest sign that time has a direction, that the future differs systematically from the past. And it has long posed a puzzle, because the fundamental laws, as we have noted, are time-symmetric, making no distinction between past and future. If the laws do not prefer a direction, where does the arrow come from? The standard answer is that the arrow comes not from the laws, but from the initial conditions, from the fact that the universe began in a state of extraordinarily low entropy, a state of exceptional order, and has been increasing in entropy ever since, simply because there are vastly more disordered states than ordered ones, so that any evolution overwhelmingly tends toward disorder. The arrow of time on this account is a consequence of the universe's low entropy beginning, not a fundamental feature of the laws. This standard account fits comfortably within the block universe. The arrow of time becomes a feature of the contents of the block, the way entropy is distributed across the time dimension, with low entropy at one end and high entropy at the other, the gradient defining a direction without requiring any genuine flow. The asymmetry between past and future is built into the structure as a pattern, not produced by any becoming. But recent work has questioned whether this account is complete, whether the low entropy beginning really explains everything about the arrow, or whether there are aspects of time's directionality that resist explanation in terms of a static entropy gradient and might require a genuinely dynamic account. Some researchers have argued that the very fact that we can record the past but not the future, that we have memories and traces of what has happened but not of what will happen, points to an asymmetry that goes beyond mere entropy distribution, an asymmetry in the relationship between events and the records of those events that might reflect a fundamental directionality of becoming rather than a mere statistical gradient. These arguments are subtle and contested, but they represent an attempt to find, within the well-established physics of thermodynamics, a foothold for genuine temporal asymmetry that the block universe cannot fully accommodate. A second and more direct line of recent work returns to the small-scale world and to the measurement problem, armed with new experimental techniques that probe the relationship between quantum systems and time with extraordinary precision. The key insight driving this work is that if temporal becoming is real, if measurement involves a genuine resolution of open possibility into fixed fact at a flowing present, then there might be observable consequences in the detailed statistics of measurement outcomes, subtle deviations from the predictions of a purely timeless account. Experimenters have devised increasingly refined tests of the time symmetry of quantum processes, examining whether sequences of measurements behave the same way, run forward and backward, whether the correlations between measurements made at different times carry any signature of a preferred direction of becoming. The results so far have been broadly consistent with the time-symmetric predictions of the standard theory, offering no clear evidence of fundamental becoming. But the precision of these tests is continually improving, and they have ruled out certain specific proposals for how temporal flow might manifest, narrowing the space of possibilities and sharpening the question. The absence of a detected asymmetry is itself informative, pushing the dynamic universe further toward the undetectable margins. But it has not closed the question, because the proposals for how becoming might manifest are diverse, and only some of them have been tested. A third line, perhaps the most theoretically ambitious, attempts to derive the structure of time from the principles of information and the relationships between quantum systems, building on the emergent time idea, but pushing it toward a point where it makes testable predictions. The reasoning here is intricate. If time emerges from correlations within a timeless quantum state, then the detailed structure of those correlations should determine the detailed structure of emergent time, including its arrow, its rate, and its relationship to space. By studying how time emerges in carefully controlled quantum systems, where the correlations can be measured directly, researchers hope to test whether the emergent time picture correctly predicts the features of time we observe, and whether it does so in a way that distinguishes it from a fundamentally timeless block or a fundamentally dynamic universe. This work is in its early stages, but it represents a genuine attempt to make the nature of time an experimental question, to move the debate from the realm of interpretation, where it has languished for a century, into the realm of measurement, where it might finally be decided. The laboratory demonstrations of emergent time mentioned earlier are the first steps of this program, proofs of principle showing that time can emerge from timelessness in controllable systems, and the hope is to extend these demonstrations to the point where they bear on the nature of time in the universe as a whole. What then of the bold claims that the block universe has been solved? The honest assessment is that these claims, when examined carefully, turn out to be claims of reframing rather than resolution, of progress rather than conclusion. The most defensible recent position is not that the block universe has been confirmed or refuted, but that the question has been transformed by the recognition that time is most likely emergent rather than fundamental, and that the debate between block and flow, as traditionally framed, may rest on the mistaken premise that time is a fundamental thing whose static or dynamic nature we were trying to determine. The genuine advance of recent years is the increasing precision with which the emergence of time can be studied, the growing understanding of how a timeless quantum substrate might give rise to the appearance of temporal flow, and the development of experimental techniques that for the first time allow aspects of time's nature to be probed in the laboratory rather than merely argued about. This is real progress, but it is not the dramatic solution that the boldest claims suggest. The frozen river has not been definitively confirmed, nor has it been overturned. It has been relocated, shown to be most likely an emergent feature of a deeper, timeless reality, rather than the fundamental nature of time itself. There is a further consideration that tempers any claim of solution, and it concerns the limits of what physics, by its nature, can tell us about the reality of temporal passage. The vivid sense of flow, the feeling that time is moving, that the present is real and the future is open, is a feature of conscious experience. And the relationship between conscious experience and the physical description of the world is itself one of the great unsolved problems, perhaps the deepest of all. It is possible that the flow of time is real, but belongs to the domain of conscious experience rather than to the domain of physics, that the universe described by physics is indeed a timeless structure, while the flow we experience is a genuine feature of consciousness that physics, concerned only with the structure, simply does not capture. On this view, both sides of the debate would be partly right. The physicists who describe a timeless block would be correct about the physical world, and the defenders of temporal passage would be correct that the flow is real, but real as a feature of mind rather than of matter. This possibility that the resolution of the block universe debate may require not just new physics, but a new understanding of consciousness and its relationship to the physical world, suggests that the question may be even deeper than it first appeared, entangled with mysteries that physics alone cannot resolve. This brings the investigation to its proper conclusion, which is not a triumphant answer, but a clarified question and a transformed understanding. The block universe arose from relativity as a natural and powerful interpretation, the relativity of simultaneity, dissolving the universal present and suggesting that all moments are equally real. It was reinforced from the side of the small-scale world, where the leading interpretations of the measurement problem, the no-collapse branching of reality, and the two-way constraints of retrocausality both point toward timeless structures rather than genuine becoming. It was deepened by quantum gravity, where time appears to vanish from the fundamental description altogether, suggesting that time is not even a basic dimension, but an emergent feature of a more fundamental, timeless reality. At every level, the trend of physics has been away from flow and toward structure, away from a dynamic present and toward a timeless whole. And yet, at every level, the conclusion has rested on interpretation rather than measurement, on choices about what the mathematics means that the mathematics itself does not compel, leaving open the persistent possibility that the flow of time is real and that our timeless theories are incomplete. The recent work has not closed this gap, but it has changed its character, shifting the debate from a contest between fixed pictures of a fundamental time toward an investigation of how time emerges from a deeper level where time, in any familiar sense, does not exist. The frozen river, it now seems, is neither simply true nor simply false. It is a description that captures something real about the structure of relativistic space-time, while likely being itself an emergent approximation, a pattern that appears at one level of reality and dissolves at a deeper one. Whether genuine becoming exists at that deeper level or anywhere at all remains undecided, suspended between the powerful, timeless tendencies of our best physics and the equally powerful intuition of temporal passage that those theories have never managed to capture or to fully explain away. The question that opened this investigation, whether the moment you are living right now is special, whether the past and future are as real as the present, has not received a final answer. But it has received something perhaps more valuable, a precise understanding of why it is so hard to answer, of exactly where the physics ends and the interpretation begins, and of how the deepest layers of reality may render the question itself a relic of a way of thinking about time that the universe at its foundations does not share. The river may be frozen, or it may flow, or it may be that the river was never the right image at all, and that what we call the passage of time is the way a timeless universe appears to those who are made of its correlations and condemned by their very nature to read themselves as moving through a structure that does not move.